Let's have a brief review on the rotating stall and surge. You remember that we said that the rotating stall is the beginning of the surge. So when the loading, for example, the incidence or angle of attack on the blade is increased, the loading is increased, we said separation occurs, and this blade can stall. When all blades stall due to the rotation, so it means that doesn't matter if one blade stalls or some blade stalls. When one blade stalls, this stall is actually mm, uh, affecting the other blades at the same row. So when one blade stalls, due to the rotation, all the blades will stall. So this means that surge will occur, and that is the disaster. The propagation speed of the stalled cell is about 50 to 70% of the blade speed. So, in other words, the whole passage would not stall at the same time. A stalled cell propagates in time to subsequent passages. You have to note that the stalled cell moves in opposite way of rotation. So, if it is clockwise rotating, the stalled cell moves in counterclockwise and then moves down to the subsequent passages. Mm, we might have this rotating stall during the startup or takeoff when our mass flow rate is low and our incidence angle is high. That's why we consider takeoff as the most demanding phase of flight envelope. And surge means complete breakdown of the entire flow field. And actually, when you are staying inside the cockpit, uh, when you are seeing the violent oscillations in the pressure instruments that are attached to your engine, it means that your mass flow rate is changing rapidly, and it means that you are getting into surge. And then you have to do something about this because it's a disaster. Okay, let's have a look at some effects of from the real fluid and losses. We know that in a real case, we have viscosity and we have turbulence, and these two are playing a major role in turbomachinery performance. Actually, in a real turbo machine, there are losses due to real fluid effects. What are these real fluid effects? The one is the total or stagnation pressure loss. And actually, this will make the entropy to increase. The We said that we have total pressure loss that makes increase in entropy. On the other hand, we have three-dimensional flow, which will make off-design conditions for subsequent blade routes. So it doesn't matter whatever you do to just avoid flow to become three-dimensional. And if you remember, what we mean by the three-dimensional is the radial actually a variation. So we said that in the preliminary design, we just have a 2D flow that is the flow that is not radially changing. So it is like it's at other radia, it is considered to be the same, but it is not. It means that whatever you do as it doesn't matter how much effort that you do, the flow will become three-dimensional after passing one or two blade rows. We also have the impact on cooling and heat transfer in real cases, so you have to take care of these as well, because so far we are just looking at the aerodynamics, not the thermodynamics. And also we have the decrease on the effective area and the pressure rise, uh, because when we are making blockage to the flow, it will decrease both of them, the effective area and the pressure size. And at last, we have the unsteady flow. Unsteady means that your lift is fluctuating. And when something is fluctuating, there will be vibration and noise. Let's have a look at the flow passage in a real turbo machine. We are just looking at the turbo machine from front view. So as you can see, this is rotating the omega, and this is one blade, and this is another blade. These blades are rotating. This is our casing of the turbo machinery. So in the passage between these two blades, that we call it the blade to blade passage, we are having different regions. A region in here that is showed by this hatch is called the end wall interaction region. We will see what is the end wall interaction region in a moment. At the corners of these blades, we are having the separation, which we call it corner separation region. We also have, in a real case, we have shear, we have viscosity, and there is a shear layer between wall and blades. And then we shouldn't ignore the secondary flows as well. What are the secondary flows? As you understand from this, let's say, sketch, the flow is kind of inside the paper or outside the paper. So what are these arrows then? These are the flows that are in secondary axis. So they are not aligned with the axial direction, and they are usually towards the tip along the span of the blades, as you can see. So they are looking like this. And if you just take a profile and you see the velocity profile, it's not, let's say, constant, and it is changing like this. It's a typical just representation of the velocity across AA, as you can see. So we will come to this in a moment. Let's have a look at the mechanisms of loss. So we said that we have some fluid effects, real fluid effects. So those will be actually generating some mechanisms that results in stagnation pressure loss. So this stagnation pressure loss, the first one is the profile loss. This profile loss is happening in blade boundary layer and wakes, and there will be loss of mechanical energy through viscous dissipation, so viscosity, and also turbulence generation. This is the main source of loss in turbo machine. So when I ask you what is the main source, it is the profile loss. We also have shock losses, and they are found in transonic regimes. Across a shock wave, you have always a stagnation pressure drop, and there is also shock and boundary layer interactions. On the other hand, you have some clearance loss. What is a clearance? The gap between the blade tip and the casing is called clearance. So we will come to this clearance in the next slide. Just keep it in mind. It's normally, the clearance amount is normally in the order of 1% of the blade span. What does it mean? It means that, I don't know if I can write in here or not. It means that if this is your blade and this is your, let's say, casing, this is your casing, when the air comes, we call this as the clearance. Why? Because this is a rotor blade and it is rotating, so it cannot we cannot attach this to the casing. So there will be some small region, small gap between the blade. So we said that this clearance will be in the order of 1% of the total span of the blade. So this is B span of the blade, so it is 1% of B. And the flow which passes from here, we call it a tip leakage flow, and or tip clearance flow, as you see in here. And this flow adds more loss to the stagnation pressure actually, so you will have actually when it is passing through here, it will create like this vortex like this, and we call it a tip leakage vortex. And this tip leakage vortex will mix with the mainstream and then make losses in P0, because it is this and this is mainstream, and then they mix and they will make losses in stagnation pressure. And what we know is that about 25 to 30% of the total loss is due to the tip leakage vortex and tip leakage loss. So there were many studies on the tip leakage flow out there. As you can see, it is shown in here. So you can see that these are the tip leakage vortex. So the flow, as you can see, this blade is moving like this from right to left. So you have some flow at the tip that is coming like this, and then it is making these vortices. And actually, it is shown for a turbine blade, but the principle is the same for the compressor blade as well. Whatever it is rotating has its leakage. So let's go back to this, what is it, diagram that I showed you before, and let's continue these mechanisms. So far we had profile loss and the shock loss and the clearance loss. Now we have a secondary flow loss, and we said that this is because of the radial movement, if you remember. So this is where that we cannot take radial flow, radial velocity as zero. So radial velocity is not zero. And we have end wall loss. So end wall loss is actually the interaction of casing and the hub boundary layer, the secondary flow, and the tip leakage flow. The interaction of all of these is called end wall loss. So that's what we show in here as end wall interaction region. So all these complex flows are interacting and making much more complicated region, which is the end wall region, end wall interaction region. Also, you have some kind of loss in only liquid handling machines that is due to the cavitation. So you know that when the pressure drops to values lower than the vapor pressure in liquid, the liquid starts to boil and evaporates. And while evaporating, you know that the cavitation bubbles are created and then collapse. When these bubbles inside the liquid collapse, they make noises, and also they make corrosion, and it means that you have a structural damage on your blades as well. Okay, we let's say actually had our discussion on different things today. So let's finish this with some examples on the axial flow compressors, and then next session we're going to start the radial flow compressors to study. So what does it say? It says consider an axial flow compressor where air at 1 bar, So the air at 1 bar and 288 Kelvin enters in with an axial velocity. So, and its velocity is 150 meters per second. This is important, axial velocity. There are no inlet guide vanes. The rotor stage has a tip diameter of 60 and hub diameter of 50 cm, and it rotates at 100 rounds per second. The air enters the rotor and leaves the stator in the axial direction with no change in velocity or radius. So no change in radius means your VR is 0. The air is turned through 30.2 degrees as it passes through the rotor. Assume a stage pressure ratio of 1.2 and overall pressure ratio of 6. Then find the mass flow rate, the power required to drive the compressor, the degree of reaction at the mean diameter, the number of compressor stages required if the isentropic efficiency is 0.85. Okay, so let's start from the basics. Basic says that you have to draw the velocity triangles, construct them. It says that there is no inlet guide vanes and the flow is axial. So it means that your V1 is VZ1. So VZ1, as the question says, it's 150 meters per second. This one is your VZ1. And the rotor is rotating with velocity U, peripheral velocity. So the W is the relative velocity with beta 1. So your alpha 1 is 0, right? Your alpha 1 is 0. And then it leaves the rotor with beta 2 and alpha 2. And the question says that there is no difference between VZ1 and VZ2, so all of them are 150 meters per second. So the mean blade speed, which is the speed at the mean radius. What does it mean radius? The question said that the radius, actually, if this is the center line, this is 50 centi and this is 60 centi, right? The hub and the tip. The hub, this is the hub and this is the tip of the blade. It says 50 and 60 centi. So the velocity, the peripheral velocity is actually your RPM times pi times r, right? So this is the actually the question said that the diameter is 50 and 60. So actually this is 25 and this is 30, the radius. So the velocity will obtained by pi times the mean radius times the rounds per seconds, which is 100, the question said. So we'll come up with this much velocity as u. Now that we have u in here and we have vz in here, then we can find our beta 1. So it is tangent inverse of u over vz, so your beta is 49.2 degrees. Then your beta 2, as the question said, the air will turn 30.2 degrees, so your beta 2 will be 19 degrees. And your alpha 2 will be obtained by this relation. So you have u minus vz tangent of beta. What is this? Actually, this is vz tangent of beta. Okay, so if you just subtract this from u, you will end up with this and this over vz. If you get the tangent, you will find the alpha 2. That's how we find the alpha 2, and it is equal to 38.92 degrees. Now we have all the angles, everything are in hand, and first let's just calculate the mass flow rate. So mass flow rate, as we know, is the rho VA, which is density times axial velocity times annulus area. What is the annulus area? If you look at the engine, or if you look at the compressor, wondering how if you look at the compressor, and these are the blades, right? These are the blades that are rotating. So the actually what we have is this area, is these two, let's say, this radius and this radius. We have this radius and this radius. So the annulus area is actually this hatched area that the air passes through. Okay, that's why this annulus area is pi over 4 d tip squared minus d hub squared. So we calculate this mass flow rate like this, and to find the actually to find there is only one unknown in here, because you already know Vz, you already know your diameters. So to find the rho, you have to do the aerothermodynamic analysis. How? You will find first of all your uh, T1, your static temperature, because your total temperature is given in the question. By using the isentropic relations, you will find the static temperature, and then from isentropic relations between temperature and pressure, total temperature and pressure, you will find T02. You know the question gives you the pressure ratio as well, so you can find your let's say T2 by knowing your T02, and also your V2 will be find from the this equation. So V axial is V2 cosine alpha 2 as well. If you go back to this in here, cosine of this will be your Vz over V2. So from here you can find your V2 magnitude. Then by knowing V2 and T02, you will find the temperature, and you have your pressure after passing. So you're using the perfect gas law. P is equal to rho RT to find your uh, density. And then you put this density in here and find the mass flow rate equal to 19.53 kilogram per second. In the next part, it says that what is the pressure, what is the power. So if you go back to your notes, you remember that we have such a definition for power. So in here, we have to do some trigonometry, because we don't know the theta one. And after doing this trigonometry from the triangles, like tangent alpha 1 plus tangent beta 1 is equal to alpha 2 plus beta 2, and so on and so forth, you will find your power equal to 412 kilowatts. What is the degree of reaction, or RD or R or DOR? Again, by going back to the relations, you will find the relation for DOR, or degree of reaction. So you find 65%. What does it mean? It means that 65% of pressure rise or enthalpy rise is done by the rotor. And in the last part, it asks the number of stages. Actually, you have the total temperature rise for one stage equal to U times Vz over Cp times tangent beta 1 minus tangent beta 2. In my notes, it was in page 10, so that's why I wrote page 10 in here in my lecture notes. So you already have this delta T0 for the stage, and then if you find it, you will find that delta T0 is near 21 Kelvin, and if you go back to the definition of isentropic efficiency, if you put the isentropic efficiency that is given to you equal to 85% in the question, you will find the delta T0 overall equal to 226.5 Kelvin. And if you divide this by the stage temperature increase, you will see that it gives you 10.79. So it means that you have to round it, so you have 11 number of stages in this compressor. I advise you to again do this calculations and everything for yourself. Also try to put these formulas aside just to be able to go fast and to find the relations. If there is any examination, these relations will be given to you, but in some other forms that you have to try to at that time you would be able to use these equations, of course. So don't worry about the equations. Try as every time I say, just try to understand the physics of these equations. This is another example. So it says we have again an axial flow compressor, and we want to design it to generate a total pressure ratio of 4 with an overall isentropic efficiency of 85%. The inlet and outlet blade angles of the rotor blades are 45 and 10 degrees respectively, and the compressor stage has a degree of reaction of 50%. So this is very common. The degree reaction of 50% means half of the pressure rise or the enthalpy rise is happening in rotor, and half of it is happening in the state. And when it is 50%, we have symmetrical blading. If you remember, these two triangles will be symmetrical. The blade speed is 220 meters per second, and the work done factor is 86%, and the number of stages required. So number of stages is it likely that the compressor will suffer from shock losses? The ambient aerostatic temperature is 290 Kelvin, and the air enters the compressor through guide vanes. As we said, when R, or degree of reaction, is 50%, we have symmetrical blading, which means alpha 1 is beta 2, alpha 2 is equal to beta 1, as it is shown in this triangle. So the axial velocity can be found from this relation. As you can see, tangent of beta 1 plus tangent beta 2 times Vz will give you the U value, right? So from this triangle, it is also can see you can see how to, because tangent beta 1 will give you this part, tangent beta 2 will give you this part, and actually this small part is equal to this small part because beta 1 and alpha 2 are equal. So is sum of the tangents times your Vz, which is this, gives you the U velocity, which is your Vz will be found at 187 meters per second. So again, from the triangles, you can find the absolute velocity at inlet, V1, and the per stage temperature rise is 29 Kelvin. Again, we have this formula, temperature rise per stage. And The total temperature at compressor inlet will be obtained by the isentropic relation. So this is T2 plus V over 2Cp squared over 2Cp. The isentropic total temperature at compressor exits. We know that you have a relation between P, let's say P03 to P02 is T03 or T02 gamma over gamma gamma. So this is actually obtained from this. Then you will find your temperature in here. This is found to be 493.9 Kelvin. The actual temperature is actually found by the compressor efficiency times this variation, which is 522 kelvins. So the total temperature rise across the compressor will be 190.74 Kelvin. The number of stages required, so we have overall temperature rise per stage temperature rise. If you divide it by the per stage temperature rise, you're ending up with number 7. And to determine whether the compressor will suffer from the shock losses, you have to find the relative Mach number. If you remember, we said that the relative Mach number is actually your relative velocity divided by gamma RT, and your relative Mach number is found by 77. 0.77, and it is smaller than 1, so it means that the compressor is not likely to suffer from shock losses. This is the third example that we have. It gives the conditions of air at the entry of an axial compressor stage, 1 bar, 314. The air angles are given beta 1, beta 2, alpha 1, and alpha 3. Alpha 3 means while it is leaving the stator, the mean diameter and peripheral speed are 50 centimeter and 100 meters respectively. Given that the work done factor is 95%, stage efficiency is 88%, mechanical efficiency is 92%, and the mass flow rate is this much, you have to determine the air angle at the stator entry, which is alpha 2, blade height at entry and hub diameter ratio, stage loading coefficient, and power required to drive the stage. So this is pretty easy. You have U over Vz is equal to tangent alpha 1 plus beta 1. So your Vz will be founded in here. And then you have again tangent alpha 2 plus tangent beta 2. So your alpha 2 will be found. Then using the mass flow rate, which is rho Vz annulus area, if you substitute, you will find the height equal to 19 centimeters. So your tip and hub diameters will be found 50 plus 19 and 15 or minus 19. So the ratio of the hub to tip is 0.449. The loading coefficient, you have the formula for the loading coefficient. You just need to put the values and substitute the values. So this is the loading coefficient. And the power required is, again, you have the relation for the power in your notes. So if you calculate, you will find it equal to 204 kilowatts. Again, I advise you to go back to your notes and find the relations for yourself, so you don't have any problem to find the equations and relations that you have to find for the problems and exercises that are given to you.